series R&D lead, and I'm here to promote SPI for you guys. So SPI, like Dom and I think the PLMs also mentioned, it's a fun program where you get to do basically whatever project you want. You get challenged by it, you learn a lot by it, and it's a lot of fun. This year I worked on my own SPI, this Tesla Coil over here, which I'll be talking about in a second, and it was a great experience. And I learned a lot of things that I didn't think I would. It's kind of even making me consider changing tracks within ECE, so there's that. But yeah, SPI, if you sign up for an SPI, you get funding, you get mentorship, you get access to our tools, our lab space, and all that good stuff. And yeah, in general, if you guys are, have any personal projects that you like to pursue, I'm all ears. I love talking to people about, all sorts of projects that, they do for fun or, as a challenge. And, if you guys want to try some stuff over summer, maybe you guys are looking for a summer project, feel free to reach out to me. I'd love to help you come up with some ideas for that kind of stuff. But yeah, otherwise, if you guys are looking for a more year-long project that would fit as an SPI, also reach out to me. I'd love to hear that, and we will definitely work something out. So yeah. Oh, wrong way. But yeah, going into it, I'll start talking about my SPI from this year. So this is my Tesla Coil, which you can see over there. And yeah, so this changed color. So today we're going to talk a little bit about what Tesla coils are, a little bit about how they work, what resonance is, how do you design a Tesla coil system, what kind of progress I made this year, and any reference material that I used. So yeah, let's get on to it. So what is a Tesla coil? How many of you guys have heard of or have seen a Tesla coil before? Okay, a good chunk of you. Yeah, so you might have seen it around probably on some random YouTube channel where they show a bunch of cool arcs. But in its essence, it's a resonant transformer. So it's a resonant transformer that produces a large voltage and beautiful arcs. And that's basically all it does. I think it wasn't discovered by, or it wasn't first engineered by Tesla, but he tried using it to wirelessly power lights. It's also, I wanted to make one because it's just a cool engineering feat. And we also needed new speakers for the lab. You can use these as speakers, and yeah, that's totally what we're gonna use them for. But no, it just looks pretty. The arcs that come out of it are pretty, so that's kind of what it brought me to do that. But yeah, talking about resonance, I'll talk about the resonant transformer and all the systems. But really quick, how many of you guys are familiar with resonance? Okay, so yeah, good chunk of you. So basically, resonance is a phenomena where we can add energy into a system by exciting it at its resonance frequency. Okay, that sounds really complicated, but one of the things that made resonance most clear to me is pushing on the swing. So if you look at the swing over here, if you guys have ever been on a swing, you push it and then it kind of oscillates back and forth, and then you push it at the right time, and then you can substantially increase the amount of energy in the system and go higher lanes. So that's kind of the idea behind it. You want to pump some energy into the system so that it kind of and for the Tesla coil, it'll overload and produce an arc. You can also see this with if you guys know the wine glass stuff where you can excite a resin or glass at its resonance frequency and cause it to break. Oops. But yeah, so this is a resonant transformer, and as such, we use LC tanks. I don't want to go over too much theory over here because you guys can look at this later and talk to me about it while tabling. But kind of think of it, it's similar to a pendulum where it does have a natural frequency, and you can try exciting it at, the pendulum is similar to a swing. You excite it at specific points in time at the right frequency, and then it'll just cause a lot of energy buildup. But yeah, so that's basically what a resonant transformer is. It's just a coupled LC tank. You guys have seen transformers used for power lines and stuff to convert higher voltage, to step up voltage into the grid, or step down from the grid into your house. If you guys don't know about that, don't worry about it. But this is kind of one way to increase the amount of voltage. and that's what's used over here. This is just it's just a transformer. So yeah, it's driven at its resonant frequency because by making it an LC tank. All right, so now let's talk about the systems engineering of this, the cool stuff. So there are lots of different ways you can make a Tesla coil. One popular one is called a spark gap. So you can kind of see the way it operates over here. You wait for this you try to charge this capacitor up to a high voltage, and then once it reaches that, the spark gap will be continuous, and then it will allow energy to flow into the transformer. And that kind of automatically dictates resonance. These are pretty cool, but also pretty scary. So that's why I did not make one of these. What I instead made was a single resonant solid state Tesla coil. So there's a lot of stuff that goes into here. I'll talk about the block diagram a little bit later, but you can kind of see what kind of arcs this produces. And versus a dual resonant, which it has the same block diagram except for both LC tanks of the transformer are in resonance. And these can produce massive arcs, but they're also really hard to drive, and you have to be very careful about them. So I didn't really try doing that this year, but maybe sometime in the future. And similar to a DRS-STC, you can kind of build off of that and get even fancier looking arcs by doing something called quasi-continuous wave. I haven't looked into this too much, so I can't really talk too much about it, but it's pretty cool. Maybe I'll try it one day, but yeah. So the systems engineering part of the Tesla coil, it's you're trying to drive this. So we take power from mains, we try to double that voltage, turn it into DC because mains is alternating current, as you guys might know, and then we turn it back into AC with an inverter. I'll explain why we do this, why we turn it from AC to DC and back in a second, and then and then that goes into the transformer and produces arcs if everything goes well. And this is kind of a topology. I'm not going to go through this, but you guys can look at this on the slide, ask me questions about this later. And this is kind of what it looks like in real life. This is a massive capacitor bank, just because of the sheer amount of current that this string draws. So and then the diode that provides rectification can be seen right there. It just charges up this capacitor bank. And so if you guys have seen a full bridge rectifier, that's kind of different from this. Full bridge rectifier, it'll convert your AC signal to 170 versus the voltage doubler topology. That's a little different, and it'll double your voltage actually. So that's a nifty thing you can use. So the H-bridge inverter, I'm gonna quickly press this video over here. So this is what I use to turn the DC signal or DC power back into AC. Basically, it's just four switches that get alternatively activated, and it will connect the terminals of whatever you're trying to power to either between positive 100 and 0, or here I use 100, but this could be 340, and then it will do it the other way around, so then 0 and 100, so then that way you can see the swing of around, in my 340 case, you can see a peak-to-peak difference of 680 volts. So it's pretty big numbers, but yeah, and let's see. And so that's what we use to basically invert the signal. The switches are replaced with IGBTs, which are special transistors for higher voltage. This is kind of what the circuit looks like. It's kind of crazy. This is the original design iteration, this one over here, and then it just turned into a massive chunk of random stuff. You guys can probably take a look at it if you come to the table. There's 28 diodes on this thing, and just the 4 transistors. So yeah, and then so the gate driver. So now we need to switch our transistors. Now the gate driver is the important part because when you switch the transistors, if you look at the inverter topology that I showed before, that seemed to make it pretty simple. But when you're actually driving the gates of these big transistors, you need special circuits for this that can ideally drive it such that it switches really fast. And that's what the gate driver does. The topology of this is something like this. This was my design for it, but there are many different designs. All this really does is it just does the switching. You give it an input signal and it just switches it around. And the reason why you can't directly supply an AC signal like a 60 hertz signal over here is because of, well, resonance, right? So you have to excite this at its own resonant frequency. The resonant frequency of this guy is around 100 kilohertz, which compared to mains, which is at 60 hertz, it's a very different frequency. So you can't really work on that. So that's why you have to do this, and the gate driver can also provide the high frequency switching. And this one is what the initial design of the gate driver looked like. It's really, really tiny, but then that's what it ended up being. I had a lot of issues with this, trying to get this to work. And if you look at this, there's a PCB, but there's a lot of stuff soldered on top of it just to try to get it to work. The interrupter is basically the thing that turns the gate driver on and off. So as we saw with the DRS-STC and like the SSTC2, the arcs it produces are quite big, and you don't really want it to be turned on continuously, otherwise it can draw a lot of current, it can heat up, there can be failure. So what the interrupter does is it just turns the gate driver on or off. So it tells the gate driver, hey, let's start oscillating and drive the Tesla coil, or it will tell it, let's not do anything and let's just let it sit there for a while so that everything gets to cool down a little. I didn't get this far because I was trying to get the gate driver to work, but I made this over-the-top design more because it's funny, not because you actually need to make it anything like this. But it's just kind of a PWM signal, which is like either off, a 0, or 1, which is on. So that's how it tells the Tesla coil to turn on and off. And yeah, so the nice thing about Tesla coils is it's very system block diagrammed. So you can kind of look at everything in the system block diagram. And this is like, you can do this for lots of things, but for the Tesla coil, it just like really drove home why it's so fun to put things in system blocks. There you can see there's the rectifier, which takes input from the mains. There's the inverter, and you can see how the inverter interacts with the gate driver through some transformers. You can see how the interrupter interacts with the gate driver, and that's through an optical link. And then the primary and secondary, those are coupled like a transformer. And when you put it all together, it kind of looks something like this. I think this is a picture of inside. It doesn't really show everything, but that's something that shows a lot of basically all of the circuits that are inside the housing, inside the coil over here. So I was making these slides at 3 a.m. So I titled this "No Context Waveforms" because I kind of got a little lazy. But I'll quickly provide some context because I don't know why I said I wouldn't provide context. That is the interrupter signal in the top middle. That's what basically, if you remember, it turns the Tesla coil on or off. And that's the signal that goes into the Tesla coil, and that's the resonant frequency. So it's quite interesting stuff. I'll show a quick demo, and it worked for 13 seconds, and I got some arcs out of it, and then proceeded to break immediately, which kind of sucked. But I got 2 videos out of it. You can kind of see the arcs on it, and hopefully I get to wrap this up next time, over summer or maybe next year. But yeah, there are a couple of things that I can fix. I do not know who put this here, but anyways, somebody's trolling me. Okay. Yeah, but there are lots of cool aspects to it. There's the mechanical stuff, there's the PCB design, electrical, everything. I've included a lot of resources and context over here, and I'm gonna try to update the Hackaday page of this post, so when you get these slides, you can take a look at that. Other than that, I want to quickly talk about some people who helped me a lot. David Zhang over there. Hello. David, thank you so much. If it weren't for this guy, I would not have been able to do any of this. A lot of people, helped me a lot for this project, so I'm really thankful. Some of their names are there. But yeah, I'll take probably questions during cabling, and then I guess I'm for Micromouse.
All right, next up is Micromouse.